is activated, it supplies voltage to a magnetic switch that stops the exposure. Number 60. Acting together, the capacitor and the gas discharge tube control the amount of time that voltage is supplied to the X-ray tube. The length of time is controlled by the rheostat, which alters the current. A large resistance lowers the current. It takes longer for the capacitor to store up charge, so the exposure time will be longer. When the technologist selects the exposure time on the control panel of the generator, the value of resistance that will result in the proper exposure time is automatically selected. Number 61. In the previous slides, we have shown how the length of the exposure can be controlled when the radiographer selects the appropriate exposure time. But there is another way to determine exposure time called an automatic exposure control system. In an automatic exposure control, or AEC system, the X-ray system senses the number of X-rays that have been used to form an image and shuts off the X-ray tube when the proper exposure has been made. The advantage of this automatic system is that it automatically allows the proper amount of X-rays for patients of different thicknesses or varying amounts of muscle and bone. Number 62. An automatic exposure control system has two main parts, a sensor and a comparator. The sensor detects the X-rays that have passed through the patient and produces a corresponding electrical current, represented by I, that is proportional to the amount of X-rays sensed. This current is then sent to a comparator. In the comparator, a capacitor stores up a voltage as long as the current flows. When V, the voltage, becomes as large as a preset reference voltage, V sub R, a switch is opened that terminates the exposure. The comparator circuit is so named because it compares the voltage with the reference voltage, V sub R. The comparator continually asks the question, is V, the voltage from the sensor, equal to V sub R, the reference voltage? When the answer is yes, the exposure is terminated. Number 63. This visual illustrates how an AEC system controls exposure time. In this simple example, both the top and bottom AEC systems are set with a reference voltage that will cause the system to terminate an exposure when two X-rays have been detected. The thick patient at the top stops more X-rays than the thin patient. Thus, the exposure continues for a longer time with the patient shown on the top. The time required to expose a radiograph is correspondingly longer. Thus, the system automatically controls the exposure time required to obtain a radiograph of either a thick or a thin patient. The same principle applies to imaging various body parts containing more or less dense tissues. Denser body parts, such as bone, require longer exposure times. Number 64. Let's now discuss two commonly used types of automatic exposure control systems. They differ mainly by the type of sensor used. The first type, shown here, uses a device called a photomultiplier and a fluorescent screen to sense the amount of X-rays that have passed through a patient. Number 65. The fluorescent screen is a device that emits visible light when struck by X-rays. This visible light then strikes the photocathode of the photomultiplier tube, and the photocathode emits electrons. The electron shown strikes a series of dinodes, with each dynode emitting 2 or more electrons from each electron that strikes it. So, after several dinodes have been struck, there are enough electrons coming out of the photomultiplier to constitute a measurable current. Number 66. The current from the photomultiplier then goes to the comparator, as previously discussed. The comparator opens an exposure switch when the voltage reaches a reference level set by the manufacturer. The main point to remember is that the AEC system is designed to stop the exposure when enough X-rays have passed through the patient. Number 67. The photomultiplier type of AEC system is usually placed to be struck by the X-ray beam after the beam has passed through both the patient and the film. Obviously, many of the X-rays are stopped by either the patient or the film in normal radiographic studies. The photomultiplier type system is calibrated to account for this loss, allowing only the proper number of X-rays to strike the film. Number 68. Here is a photograph of an actual photomultiplier type AEC system sensor. As with most electronic components, it does not look exactly like its diagram. In this particular photomultiplier, visible light would enter from below. Electrons would then be directed internally, exiting the tube through pins shown here on the left. The comparator and its associated circuitry would be connected to this tube. Number 69. The second type of AEC system is the ionization type. The sensor of this system is called an ionization chamber. The chamber produces an electrical current when exposed to X-rays. This current is then sent to the comparator, which, when a sufficient amperage is built up, opens the switch and terminates the exposure. Number 70. When an X-ray strikes the gas in an ionization chamber, it knocks electrons out of the gas molecules, as shown at the top of this visual. These electrons are then collected by a positively charged central electrode and are sent on to the comparator as a current, I. Number 71. The ionization type AEC sensor can be made of materials that are nearly transparent to most X-rays. The chamber is usually placed between the patient and the film, allowing it to produce more current than if it were behind the film. The current is then passed through an amplifier to provide a strong signal to the comparator. On the right is a typical wall-mounted chest cassette with 3 ionization type AEC sensors. The signals from any one sensor or a combination of all 3 sensors can be used to determine exposure time. Number 72. Now let's discuss how to calculate the power rating of an X-ray generator. In Lesson 3 of this series, we introduced the concept of electrical power. You will recall that power is measured in watts. To determine the number of watts in a circuit, we multiply the current, measured in amps, by the voltage, measured in volts. X-ray generators are rated according to the amount of power they deliver. Since modern X-ray generators can deliver thousands of watts of power, the maximum power rating of a generator is usually given in terms of kilowatts, 1 kilowatt equaling 1,000 watts. Number 73. Technique factors set by the technologist on the control panel of an X-ray generator are expressed in milliamps and kilovolts. Each milliamp equals 1,000th of an amp. Each kilovolt equals 1,000 volts. When we multiply milliamps times kilovolts, we obtain watts, units of power. Number 74. To obtain the power rating of an X-ray generator in kilowatts, you first multiply the milliamps by the kilovolts, then convert the watts to kilowatts. To do this, divide by 1,000, since there are 1,000 watts in each kilowatt. Thus, we have a final formula for finding the power rating of an X-ray generator. Multiply the milliamps by the kilovolts, and divide by 1,000. Number 75. Let's look at some examples of X-ray generator power ratings. If a manufacturer says that his generator is rated at 150 kV at 300 mA, the power rating in kilowatts is 300 times 150 divided by 1,000, or 45 kilowatts. The same generator may be rated at 125 kV when the MA is 1000. The power rating is then 1000 times 125 divided by 1000, or 125 kilowatts. Power rating of a generator, you must know the maximum MA that the generator can deliver at a given kVp. 6. Modern X-ray equipment manufacturers build protective circuitry into their X-ray generators. For example, if the generator is rated at 150 kV at 300 MA, then it is rated at 45 kilowatts. However, if the technologist selects 150 kV and 1000 MA as technique factors, the exposure would call for 150 kilowatts. If the generator is equipped with protective circuitry, a warning light will flash, and the X-ray generator will not operate. In this way, the generator and the X-ray tube are protected from overload. Number 77. There are other circuits in an X-ray generator that allow it to operate more efficiently than the simple circuits we have discussed. Some of these circuits are the circuits for the kV and MA meters, the circuits that compensate for sudden changes in main line voltage, and the circuits that compensate for resistance due to cables and switches. Microprocessors, small computer circuits, are used for many purposes in newer X-ray generators. They can be used to time exposure, determine heat loading, and to pre-program kVp and MA settings. You should at least be aware that these circuits exist, but we will not cover them in detail. Number 78. You have covered a lot of new material and seen many new circuit diagrams in this lesson. A quick review of the purpose of the X-ray generator may help you to organize the material we have covered. The purpose of the X-ray generator is to provide the voltage and current required to operate the X-ray tube. The various circuits in the X-ray generator allow the radiographer to select the technique variables, kVp, MA, and time. Number 79. The kVp is determined by the components in the tube circuit of the X-ray generator. The number of loops in the auto transformer and the step-up transformer determines voltage. The step-up transformer has a fixed turns ratio, while the auto transformer is variable, depending on the kVp selected by the technologist. The rectifier circuit allows the tube to use the AC voltage more efficiently by converting it to DC. Number 80. The MA is determined primarily by the components in the filament circuit. The rheostat is a variable resistor that controls the amount of current that reaches the step-down transformer. The step-down transformer, utilizing a fixed turns ratio, steps down or decreases voltage and steps up or increases current. Number 81. The exposure time, the length of time that X-rays are produced by the tube, is controlled by circuits that are usually located on the primary side of the tube circuit, on the primary side of the step-up transformer. Timer circuits are usually on the primary rather than the secondary side of the circuit because the voltages are lower there and the circuit is more easily interrupted. An alternative to a timer set by the radiographer is the automatic exposure control system. In the AEC system, a sensor located near the image receptor stops the production of X-rays when a sufficient number of X-rays have penetrated the patient. Number 82. You are now ready for Review Exercise C in your student workbook, covering X-ray timers and generator power rating. When you have completed the exercise, turn to the answer page at the end of the Review Exercise section and check your work. Then restart the tape. Stop the tape now. You should have completed Review Exercise C and checked your answers. If your score is less than 80%, You should review this material before proceeding to the self-test for Lesson 5. A score above 80% indicates that you are mastering the material.